come to the second presentation of this session. There is a change in the speaker, so Zoltán Kovács will present. I believe the title is the same, so I can read it out. Topology of Quartic loci resulted from the lines passing through a fixed point and a conic. Please.
Good morning, thank you so much for your interest in coming. My name is Zoltán Kovács, and my colleague, Professor Dana Pika, had to go back to Israel because of some urgent family reasons, so I will deliver this talk. He and our third author, Professor Young from University Radford University, USA, we are from the teaching part of mathematics, so we work in education, and the problem, this topology problem, came from Chinese entrance exam. It's a kind of generalization of this question, and to be honest, we are not experts of studying curves or surfaces. We like the topic and we try to apply some methods. We use two methods for studying this problem, and the sub-results are not there. The one method is Gröbner basis, and the second one is the Gröbner cover. I think some of you know these methods. In a nutshell, the problem is there is a fixed point somewhere. This is the fixed point. Yes, exactly. In the plane. So this is a planar problem in 2 dimensions, and we have a conic that is usually an ellipse, and we put 2 points on this ellipse C and D, such that the point C and D, you cannot see it in this figure, just later, C and D and A are collinear. So these 3 points A, C and D are collinear, and then we choose a number S. This is a given real number, which is a dilation factor, and we dilate the segment CD in a direction which was given by the number C, and then we get point E, and the locus of the point E is interesting. So maybe you can have an idea what happens here when we study this thing. This is something like that. So again, we have an external point somewhere, E, A, and conic. In this case, the conic is a circle. Points C and D are on the circle, on the conic. And then we have a stretching factor. This is called S, and the stretching factor creates the point E. And when we choose different points D, then of course point C will be also different, and E will be kind of locus. So this is a quartic curve. It was drawn with GeoGebra. It is an implicit equation of the curve, and after some programming for GeoGebra is an educational piece of software, we managed to create a symbolic version of the command delete that dilate command was extended to give some symbolic support. So that's why we can get the implicit equation of this curve. Some other types of the curve that can be obtained when we have different stretching factors, and you can see that the topology, in the sense topology, we have sometimes an 8-form curve. This is one topology, kind of topology, and otherwise the curve looks like a drop, so no longer an 8-form. The question was, where is the topology changing? It's a very simple question, but if you have a difficult curve, for us at least it was difficult, a quartic curve to study, you go into difficulties. The first question, maybe we can do it graphically. So just let's zoom in and we can see that while the curve is behaving strangely here, and numerical algorithms that try to visualize the curve, they are not always accurate. So here, for example, you can see some noise. Maybe I just use my mouse. Okay, so here there is some noise in the picture, and if you use some very sophisticated methods like real geometry, so here we are using cylindrical algebraic decomposition, which is a new approach in GeoGebra, and its fork version GeoGebra Discovery. When we use such real methods that can be slower, or in some sense they can be fast enough, then you can learn that the curve is really like an 8 form when the stretching factor is minus 0.63. Okay, so how to handle the situation? Mathematically, we do some algebraization. First of all, if we consider a special case of the problem, we can assume that we have a circle and we can put point A on the y-axis. So this is a special case, and we can simply define the equations for the circle, for the collinearity, for the dilation, and then by using elimination, I think it's well known among many of you, via elimination we can get an elimination ideal, and finally, to find the critical points or singular points or something like that, we can compute the derivatives of the obtained parameterized curve with respect to variables x and y. So this is the system, this is the concept, not just for the circle, but also for the ellipse. Mathematically, these are the equations, quite simple for the first look. For the collinearity, we use the determinant to describe the area, the degenerate area of a triangle, and for the dilations, it's quite simple to express the coordinates in linear forms, then the elimination, and then we will consider some factors of the polynomial that was found. Okay, so this is a program written in a computer algebra system called GIAC, made by the French mathematician Bernard Paris. He is a volunteer of writing nice computer algebra systems, and this is a free one, and it has a very effective method for elimination and also for granular basis computations. So this is the code, and if you compute it, it's not so difficult, which in Mario's slide, so the 17 lines of polynomial, but it's also a bit complicated. It's just a degree of 4. And the first factor is a degenerate factor, and the second one is a quartic, which has some parameters, so you can have an idea what happens. But if you want to learn what the second factor means, there is a black box strategy in GIAC, in this computer algebra system, that can use the command solve. Solve does something we don't actually know what kind of techniques here are used. I guess Bernard is in the background. So these are the solutions. And you can see that the third solution, this plus minus, this orange one, is some strange solution. Why is it strange? Because we expect that the singular point or the critical point is on the y-axis. And in this case, it's not. So the reason is that the algebraization, the algebraic translation is not a one-to-one translation, and sometimes, or many times, you get additional information, piece of information, so you have to be careful and somehow to filter out these non-geometric components or non-geometric solutions. So the other ones, however, are really useful, and if you visualize them, this is one degenerate component, another one, and this is actually the topological border case when the drop form turns into an 8 form. So this can be computed by using Gröbner basis. Yes, some other degenerate cases. The generalization, if we want to do the same for the ellipse, it's not really difficult in the terms of algebra. We only have to have a q greater than 0 assumption, and the technique is actually the same. The problem is very similar, and we have again a quartic for the second factor, and of course some more parameters, because we have a more general question. So if you solve this, then the answer, the computer-based, the computer-delivered answer is more difficult, and the orange parts are again nonsense in geometry. Meaning, why? Because, for example, under the square root, you can see minus q. So this is something non-real thing. We are playing in the complex plane when we are using the Gröbner basis at this point. Okay, so we can have for special numbers A1, A2, and Q special results, but unfortunately, when we have a full generalization, the computation of the Gröbner basis becomes too difficult. Unfortunately, and we need to mention here the RISC Institute, very close to here in Hardenberg, 15 kilometers. They offered a computation system for us, but after 130 gigabytes of memory resources, and one day we stopped. No, we don't want to kill that computer in Hagenberg. So we can go into similar problems like Mario and his research team. So no, it was not a good option. Then we had a second idea, not the sub-resultant way, but another wonderful piece of software written by the Singular people from Germany, and another researcher, Antonio Montes from Barcelona. This is the so-called Gröbner cover system. I think many of you know this Singular program, also free piece of software. There are very good books on it. And what we expect here, again, because it's still a complex number-based approach, we need to find a needle in a haystack. And literally, we need to filter the output for certain variables. We just use the Unix grep command to filter the variables, and then when we have the results, we obtain them, then we need to find a good factorization to learn the geometric meaning. So this is the output for Singular, just 16 kilobytes of output, not very big, but really like a haystack. It's a haystack. I have 12 slides for the output, but luckily already the first mesh, the first polynomial that was delivered by the Singular was helpful, because we managed to form this in another expression that gave us a useful result, and it had also a kind of geometrical meaning. If we use the manual of Singular, the output is given in such a form that the union of geometric varieties and some sets that are removed from that variety, this is how it is given. So we have, first of all, an algebraic interpretation, and second, we can convert it into a geometric interpretation. So, but this is also kind of work, intellectual work. Now, even if we have an algebraic statement, we should check the geometric counterpart, and finally, by using a third method, and this was only pure thinking. sometimes teachers have to use their head, not just the computers. We had an idea how to avoid computer algebra, at least the Gröbner cover, only just the elimination technique by using Gröbner basis. So this is how it is, and I think I can show it in 2 seconds. This is the general case, then I stretch, or we stretch this general case into a circle, and then we rotate this to have something like that. So we can use our head and some kind of intuition to solve the general problem by only elimination and not using the Gröbner cover. A final word maybe, we are, as said, education people and not really researchers of computer algebra or geometry, but we found that discovering and having a conjecture and then proof, it was really an intellectual challenge, and maybe some of you can suggest us some better approach to do it in a more general way, because, for example, in a 3D generalization, the equations are still too difficult, so we don't do anything about the 3-dimensional case. So, thank you very much. That was.
Thank you. Please, your questions.
Maybe, I don't know if I understood well, but you said that you obtained some weird singular bonds, the exponents of those not equal to 0.
Yes.
So.
Yes. Shall I show that slide maybe? 1 second. Here, I think this is.
Wait, maybe the question is because it's a rational Quartic curve, it has three singular bonds. And typically two of them will be the product. So might it happen that this is the case, or?
Yes, I think so.
Okay.
Yes. Okay, thank you.
Further questions? Well, I think you already asked the question, so maybe.
I think that these stranded factors that you get, you can control them from the beginning. You have to exclude probably something like the isotropy in the construction. So these phenomena that happen with the circle and afterwards with the ellipse, I think that you can control them in advance.
Thank you. Maybe we tried that kind of approaches, but finally we couldn't do any simplification. So it was the simplest way. But maybe you know this situation.
Yeah,
so will we ever have this question in the Austrian Zentralmatura?
If it's a good question, we hope. Maybe not this one, but a simplified version of.
For the sake of my sons, I hope not. It's a good kind of question. What should I ask you?
So, she was actually said before, so what is meant with when you consider two recursive equivalents? So I guess it is up to diffeomorphisms of the plane, which means one curve to the other, because you want to also preserve that.
Yes.
Yeah. So then a follow-up question is, how would you explain this to students when two curves are the same, because they are diffeomorphisms?
The original question was not about topology. It was a simpler question to compute it in a special case. So I think for the Matura it will be also too difficult to find the topology. So it's a kind of second question. It's a kind of generalization among us. Well, maybe we can do some more experiments and give to students who are interested and want to do experiments.
Further questions? I would have a comment because you mentioned the spatial case. So basically, I believe that your definition of this curve is a finite invariant, and actually you showed it to us. You can transform the ellipse into a circle and thus get a finite equivalent version which is much easier to compute. But you can do the same thing in space. You can transform the ellipse into a circle and then have a special point A, so they have a rotational symmetry. So basically the spatial case is up to a fine transformation, just a rotated version of the planar version, I would say. So that should be quite straightforward, which of course leaves the question, there's a difference, probably a difference between ellipses, hyperboloids, and paraboloids, which might need a different investigation.
Thank you for the suggestion.
There's room for discussion. Okay,
Thank you.
thank you very much.